Hi guys, good morning. I'm a little late. Sorry. Every one of you is here. Start right away. So we have been seeing different types of isomerism, right? So I think we've completed tautomerism. I think last class we saw geometrical isomerism, cis and trans, and I told you how it works when I have C double bond C, or when you have a cyclic structure. There you can have geometrical isomerism happening. And I told you what are the conditions in which the C double bond C compounds will give geometrical isomerism. I told you that when you have a C double bond C and you have two other bonds on the carbon, two carbons, they should be different. Only then you can talk about geometrical isomerism. If not, that compound is not capable of giving geometrical isomerism. Right? Okay, fine. So we'll move on. So we have completed all the major types of isomerism, right? Actually, what I forgot to tell you is when I go for this stereoisomers, right? So I told you that they can be classified broadly into two, that is geometrical and optical. Actually, there is one more way by which I'll be able to segregate them, right? So first, that one is what is called as constitutional. Constitutional isomerism, and the other one is conformational isomerism, right? This is not I people. This particular thing is O, right? Conformational. This is N, right? Conformational isomerism, right? Now under this constitutional, again I have two types. That is your geometrical and optical. Okay, so this for first thing, these two are the broader classifications, and under constitutional isomerism, I'm going to get geometrical and optical. Right, geometrical and optical is going to come under constitutional isomerism, and under conformational I'm going to see what is going to come, right? So this we have completed. I mean, optical isomerism I told you we'll see in 12th class. Geometrical isomerism we have completed, right? Now what about this, right? Now for constitutional isomerism, right, as I told you, these are because of the orientations which I am going to put in paper, right? As I told you, when I have C double bond C, right? When I have C double bond C, so these two bonds, for these two carbon atoms, there are two bonds exactly. So where I'm going to put the this thing and this thing, the other groups are going to depend upon me, isn't it? Again, I can write it on paper. But again, in this case of conformational isomerism, right? So this happens when I have CC single bonds. Okay. Now, as I told you, these CC single bonds can undergo a rotation, isn't it? This CC single bonds can undergo rotation, and because of this, again, I can see that there are going to be three more bonds for each of these carbon, right? And obviously, the 3D orientations are going to be different at different point of time. Please understand that this is going to happen in reality, just like tautomerism, right? This conformational isomerism is going to happen in reality, right? Because we obviously know for sure that the single bond, CC single bonds can rotate, right? So if it rotates, obviously the three groups here, the three groups here, right? All of them will have different orientations in 3D space. Again, at a particular point of time, you like what to say? We'll see. Okay, right, fine. So actually, it is better if I take an example. It is better if I take an example and explain you, right? So, right. So for me to explain, let me take normal, simplest of all molecule. Let me take ethane molecule, right? So ethane I know is CH3, CH3. Done. So again, you see this carbon and this carbon is attached by a single bond. That means this bond can rotate. Okay, right. So for me to visualize the conformations, right? The isomers are what are called as conformations or conformational isomers, right? So if you want me to visualize that, there are two ways of visualizing it, right? So one is what is called as your, I think you should have seen it, Sawhorse projections, and I have something called as Newman's projections. Okay, Sawhorse projection and Newman's projection, exactly same things, right? It's just that how am I going to represent it is going to be different, right? Okay, so I think Sawhorse projection and Newman's projection. Okay, fine. So anyways, we'll see what it is, right? So in case of Sawhorse projection, people, right? So how will I represent this compound? It's just, this is also a way of representation. Like whatever I wrote here, this is also a way of representation. The other way of representation is like this. Like if I just put a line, again, this represents a carbon, this represents a carbon, right? So all now again, I'm going to see a different way of writing here, like representing the compound here, right? So how am I going to represent is, say, first I put a dot. Okay, now this dot represents one carbon atom. Okay, and I am going to put a round, I'm going to put a circle, and this represents another carbon atom. So what you see is this dot is coming towards you, right? And that is the first carbon atom, or we are going to see this is the planar way of looking at it, right? Now if you just flip the compound and you put this carbon atom to face towards you, right? This carbon atom, if you just turn it and if you just place it towards you, obviously this carbon atom will be away from you. I mean, I'm just talking about towards you in a sense, this is going to come out of the screen, right? So that is what is being represented here. The dot represents that the carbon atom is going to come towards you, and the round represents the carbon atom which is going to be inside the plane. Okay, so one carbon is represented by the dot, and the other carbon is represented by the circle, right? Okay, so let me draw it. Okay, better, right? So now I have to represent the hydrogen atoms also, isn't it? Right, now you make, fine, I'll make the hydrogen atoms. So for the first carbon atom, the dot carbon atom, let me make the hydrogen atoms. So first hydrogen, right? Second hydrogen, and the third hydrogen. Okay, right. Now obviously for the next carbon atom also I have three more hydrogens, right? Now assume that the rotation has not started yet, or you can assume that there are going to be this three hydrogen atoms, and the other carbon atom also is going to have three hydrogen atoms. Assume that I'm going to start at a position where these all the six hydrogen atoms are in the same line. Okay, all the six hydrogen atoms are going to be in the same line. I just started there for my reference point. That's it. I can start anywhere, right? So I'm going to start putting the hydrogen atom in a place where all the six hydrogen atoms are going to be in the same line. Okay, now how will I put it? So it's pretty easy. So for this carbon atom, right, for this carbon atom, I'm going to put a hydrogen, one hydrogen here, right? Again, for the hydrogen atom will be here, right? And you see the hydrogen atom will be here, right? Now what you see is, right, if you look from the top, if you look from the screen, right, basically you see that this carbon atom is coming towards you, the other carbon atom is behind the plane, right? So if you just see from the front, right, you will be able to see only three hydrogen atoms. Hope you understand what I'm trying to say, right? Even if you just see from the front, right, you will be able to see only three hydrogen atoms, because all the other three hydrogen atoms are exactly in the same line as in the case of previous hydrogen atoms. So if you look from the front, right, you will be able to see only three of the hydrogen atoms, that is in the first carbon atom. The other three hydrogen atom which is behind, you will not be able to see them. right? So this is one of the confirmations. Again, basically this has not started, or I would say this is one of the positions when the rotations happened, right? So this, since you're able to see, so it's like someone is just shadowing the other one. It's like an eclipse, isn't it? Like whenever a lunar eclipse, a solar eclipse happens, right? What happens? One thing comes over the other, and you'll be able to see only one thing, isn't it? So this kind of confirmation is what is called as eclipsed confirmation. Right? It's called eclipse confirmation. You can see how is it, why is it called an eclipse? Eclipse means one thing shadowing other, right? So these three hydrogen atoms are going to shadow the hydrogen atom which are behind them. Will not be able to see them at all, right? That is eclipsed, right? Now, say I now start the bond starts rotating. That is the single bond which which is stated here. This one, right? This bond which I have is going to rotate, right? Now you can keep one thing as a reference. That is, say you maintain the first carbon atom to be a reference point, right? And you rotate the second carbon atom, say this way. You can rotate however you want, right? You can even rotate this side, or you can even rotate this side, no issues. But anything, it's up to you however you want to do it. I'm doing it this side. Okay, the arrow mark which is mentioned here, that way I'm going to rotate it. Okay, now actually people, at each, and I can say, if I'm going to look at all the possible positions of this of these three hydrogen atoms, this three, like with the inside hydrogen atoms, if I'm going to look at it, right, if I'm going to look at all the possible things, how many do you think I'll get? How many confirmations do you think I'll get for all the possible points? If I take, how many possible points do you think I'll get? Hmm? How many points? I'm actually going to get infinite number of points for, if I say 0.1 degree, obviously there'll be a difference between these two angles, right? Say another 0.1 degree, another angle. So like this, I can have thousands and millions of confirmations possible, but I cannot study about all of them, isn't it? Right? I can study about certain things which are important to me, right? Because every degree, every 0.1 degree, every 0.01 degree of rotation is really not going to be helpful for me, right? So this is one extreme case, the eclipse which I've done here, right? This is one extreme case, right? Now we'll see what is the other extreme case, right? And but in between these two, you have again infinite number of possibilities, right? But we are going to look at only the extreme cases, right? This is the eclipse case, right? Now, when I look at the next case, right, when I'm going to look at the other case, say now again, I make the first carbon atom dot, okay, second carbon atom around, right? Now I'll just place the hydrogen atoms in the front carbon first. Okay, three hydrogens, done, right? Now I have rotated the other carbon atom. I have rotated the other carbon atom, say by 60 degrees. Actually, why specifically 60 degrees? You will understand, because that is the possibility, right? That is the other end of the possibility, the next extreme possibility, right? So if you do that, can I say this hydrogen atom would have come here? That is, I'm talking about this one, right? This hydrogen atom would have come here, and this hydrogen atom, oh sorry, this hydrogen atom would have come here, right? And you see this hydrogen atom would have gone here if we just rotate the second carbon atom by 60 degrees. Okay, now you see, if you if you look from the front, right, and all the 6 hydrogen atoms are completely visible, is it not? But in the previous case, if you look from the front, I was able to see only 3 of the hydrogen atoms. Correct. But here you will be able to see all the 6 hydrogen atoms. And this particular confirmation is what is called as staggered confirmation. right? This conformation is what is called as staggered conformation. This is eclipsed. When you're not able, we are able to see only 3 of them. And if you're able to see all the 6 of them, it is going to be called as staggered conformation. Okay, right. Now the next question is, which is stable? Which is more stable? Eclipsed or staggered? You tell me.
Eclipse.
Why? Okay, fine. So again, whenever you this kind of questions come, now as I asked you the same question in case of cis and trans, which was more stable? In case of cis and trans and geometric isomers, which was more stable? Which was more stable? Cis and trans.
Trans.
Yes. Why? Trans is the most stable one. Why was trans more stable? So if you place the two groups opposite to each other, why it makes it more stable? Anybody else? Anybody can give me the answer. What is the thing? What did I tell you? I mentioned this point, isn't it? When they ask you cis and trans, which is more stable, you should tell trans is more stable. But what is the reason? Nobody remembers. It was just yesterday's class, people. How can you not remember? Okay, so the reason is repulsions, right? So when I'm going to place the groups opposite in the opposite places, right? Obviously, the distance between them got increased, right? So obviously, the repulsions between the bond pair of electrons also got decreased, right? Distance increases, repulsion decreases. Okay, so please remember this point. Why trans is more stable? It's because of lesser repulsion between the groups, because you have increased the distance by placing them in the opposite sides. Yes, understood? Yes, no?
Yes, understood.
Okay, fine. So the same reasons can be given here. Okay, so now you see the hydrogen atoms are very, very close by. That is an eclipsed, but hydrogen atoms are as much as far away from each other. This is the other extreme case. The hydrogen atoms are closest, the hydrogen atoms are farthest from each other. In eclipsed, they are the closest. In staggered, they are the farthest. And obviously, which is more stable, the answer would be staggered. Again, because of the same reasons, repulsions. Right? Again, because of the same reasons, repulsions. Right? This was going to have lesser repulsion when compared to this. Again, the reason is because the hydrogen atoms are very close. Here, the hydrogen atoms are very far away. I mean, the maximum possibility, they're very far away from each other. Okay, so I think this is Sawhorse projections. Newman's projection, how do I do it? I think I forgot. Newman's projection, I think.
I have a doubt. So both of this comes under Sawhorse projection. So both.
See, basically projections. What do you mean? This and this again. In case of Newman as well as your Sawhorse, you are again going to get the same thing, eclipse and staggered, right? But how do you represent it is just going to be different, right?
Okay.
So here the representation is like this: one dot and one round. There, I think it's different. I forgot what was it. Newman's projection. What was it? What was the other way of representation? I forgot. What did I do? What did I do? Okay, fine. Anyways, it is not a big deal, right? So anyways, I'll tell you in the next class. Not a big deal at all. But again, same thing you're going to get. Right? Because the way of representation is going to be different. Again, you're going to get eclipsed as well as staggered. But the way of representation is going to be different. That's it. Right? But anyways, I prefer this only. This is an easier method. I would prefer Sawhorse method only. Right? When someone asks you in the exam, right, write the eclipsed and staggered conformation, and they don't tell you anything regarding Sawhorse or Newman, you prefer to go for this. This is a little more easier when compared to Newman's, I think. But I think it is also gonna be easy. It's not that complicated. But anyways, I'll tell you next class. Not an issue at all. Okay, right. So this is all. This is what about what is that conformational isomer? But this is not the only case, guys. If I'm going to take a little more complicated molecule, say I take butane, right? I take CH3, CH2, CH2, CH3, right? Now, you have to look at, I mean, obviously all the single bonds can rotate, no issues at all, right? But if we take this bond, the first bond, again, it is going to be similar as the previous case, right? Because three hydrogen atoms, two hydrogen atoms and one carbon atom. But then the better way of looking at it would be, I mean, better way of, if you want to understand conformational isomerism, it's better you look at this bond, the second bond. Okay, so we'll see what happens there. How do you represent? Same way we'll try to represent. Okay, so let me put a dot, right? I'm talking about this carbon and this carbon, people. Okay, so dot, which is coming towards you, another bond which is inside the plane, another carbon atom which is inside the plane, right? So let me mark what is there in this carbon atom first. So you see there are two hydrogen atoms and there is a methyl group, correct? Right, there are two hydrogen atoms and a methyl group for each of these carbon atom, right? Okay, so H and a methyl group, right? H and a methyl group. Same thing is there for another carbon atom also. For this carbon atom also, this is the same thing, H and CH3, right? Again, you start with eclipsed. Okay, that means what? The H's are gonna coincide, right? And the methyl group is also going to coincide, right? So if you look from the front, right, you will be able to see two hydrogen atoms and one methyl group, because all the other three are going to be inside and exactly in line with the first one. So you'll not be able to see them, right? Okay, so this is my eclipsed. This is my eclipsed. Okay, now I'll give you 10 seconds time. Try to draw the staggered conformation. Quick. Okay, hope you're drawn it. Anyways, I will try. Right now, I'll just go step by step. Let me rotate it by 60 degrees. Okay, I am going to rotate this by 60 degrees. Now, what will happen? Let's see. So, dot uh, carbon. So H. Oh, this is CH3. Okay, right. Now, if I rotate by 60 degrees, now what happened is this hydrogen atom would have come here. Okay, this rotated by 60 degrees. This hydrogen atom would have come here, and this hydrogen atom would have come here, right? And the methyl group which is here would have gone here. Okay, right? Yes, this is what happens when I rotate the bond by 60 degrees. But can I call this as staggered, the structure? Hmm? Can I call this staggered? Yes, no. Okay, let us take a vote. Guys, okay, I mean, let me show you the structure first, and then I will. Okay, right. So I can see the structure here, right? So how many of you think that this can be called as staggered? This is the staggered conformation. How many of you say? Quickly, put it in the chat, or you can open your mics and talk. Quick. It's just a guess. You don't have to be correct. I mean, if you're right, okay, wonderful. So yes or no? Quick, quick, quick. Can this structure which I drew now, after rotating the bonds by 60 degrees, can I call this staggered? Hmm. I know all of you are there. I can see you guys.
Yes, sir. It can be called.
Okay, so one vote that we can call. Rohan says, okay, well, I have one in the chat. Vanisha says, yes, sir. Okay, two votes. Quickly, guys. Others, I have, I think, Abhishek, Divya, Mithun, Pranav, Rahul, all of them are there. Okay, Pranav says, yes, sir. So 3 votes. Okay, Divya also says yes. Okay, fine. Okay, so most of you say yes, right? Okay, now, what happened in the last case when I took ethane? Now, what do you see here? When I say staggered, right, you are seeing that all the hydrogen atoms are exactly opposite. Say, for example, for this hydrogen atom, this is the staggered hydrogen. Same way, for this hydrogen atom, this is the staggered hydrogen. Same way, for this hydrogen atom, this is the staggered hydrogen, right? Exactly opposite. Okay, right. So now we'll see what happens in this case, right? Now, for this hydrogen atom, right, where should have been the staggered hydrogen? It should have been in this place where the methyl group is there, right? Again, for this, it's okay. This and this are completely staggered. I accept, right? But what about this hydrogen atom? This hydrogen atom should have had a staggered hydrogen here if this was staggered. And now, if I consider my methyl group, this methyl group, if I consider for this methyl group, in this position, the methyl group should have been there. Then only it's staggered. Hope you understand what I'm trying to say, right? It should be on the completely opposite side, whatever the groups you have, right? So this is not staggered, people. This is going to be somewhere in between staggered and eclipsed. It is these kind of structures are what are called as skew structures or gauche structures. I don't think you have this in the syllabus, but there's no point in learning something new. Not a big thing at all, right? So you just write it by 60 degrees, right? And obviously this is not staggered. I told you what can be staggered. It should be on the exact opposite sides, each and everything, right? So you see the methyl groups are far away from each other, but is this the farthest position can I get? No. The farthest position would have been if this methyl group would have been in this position. That would have been the most farthest, that is the most amount of distance I can have between the methyl groups, right? So this is not, so this is eclipsed, okay, completely all right, because you see all of them are together, right? Now this is because they are the closest. Now these are not the farthest, these are somewhere in between. So all these in between structures are going to be called as skew or gauche structures. Okay, now do me a favor, rotate again this bond by 60 degrees and draw the confirmation what you're getting. I'll give you 10 seconds time. Quick. Rotate the bond by 60. Keep the front carbon same. Don't change anything. H, this CH3, and this H, don't change anything. The behind carbon atom just rotate by 60 degrees.
Sir, we are getting staggered, sir.
Will we be getting staggered? We'll check. Right. So now when I put it, okay, let me put the first carbon atom first. Remember, in staggered, I have to get the maximum distance between the groups. That's what I need to get. Okay. Right. So first, hydrogen. This I'm not disturbing at all. The first carbon atom. Right. Now, second carbon atom, now I have rotated by 60 degrees. Oh, this is not a H. Sorry, this is CH3. Okay. Okay, this is CH3. Right. Now, if I've rotated by 60 degrees, now what would have happened is this methyl group which I have here would have come here. Right. And this hydrogen atom which I had here would have come here. Right. And this hydrogen atom which I had here would have come here. Yes or no? 60 degrees. Just think about it.
The 60-degree means that H will go to the other H position, no, sir.
Yes, this H would have come to this position. Again, this H would have come to this position. That's what would have happened. 60 degrees. Yes, no, understood. But anyways, guys, if you don't understand that how much degrees I'm rotating, so now just tell me, is this confirmation staggered confirmation?
It's eclipse, sir.
It's not eclipsed also, right? How is it eclipsed? Okay, these two hydrogens are eclipsed, but what about these two? No, I have a H and a methyl group there. It is not eclipsed, right? So again, this structure is called as a skew structure. Whatever is in between, I have only three types of things: eclipse, stagger, and skew. That's it. Okay. Now I will rotate it by another 60 degrees. Guys, if you don't understand how am I rotating by 60 degrees, don't have to worry. Nobody, I don't think they will ask you this question. Right. Okay. So again, I draw H, H, and CH3. Right. Now I have rotated this by 60 degrees again. Okay. Now what would have happened? This methyl group would have come here, and this hydrogen atom would have come here, right? And I have another hydrogen atom here. This would have come here. Now tell me, is this staggered? Is this staggered?
Yes, sir.
Yes, it is staggered. Now you can easily see the methyl groups are from the farthest from each other. Methyl group on one side, exactly opposite side I have methyl group. Hydrogen atom here, hydrogen atom exactly opposite. Hydrogen atom here, hydrogen atom exactly opposite. So this, guys, is my staggered confirmation. Okay, this is what is my staggered confirmation. Now you see how many 60-degree rotation we require for us to get eclipse to staggered. First 60 degree here, second 60 degree, third 60 degree, then only you are getting staggered confirmation. And you can see what are the difference between all these structures. Okay, so if you practice it easy, it's pretty easy, guys. 60 degree, you maybe it's when I say 60 degree, you're little getting confused, but you don't have to worry. Okay, right? So, and this is just for your understanding. If you had understood this eclipse and staggered, that is in case of your ethane, I think that is what is there in your book, in NCERT textbook. I don't think you have more than that, right? And I can complicate it more. I instead of this two hydrogens, right, I can put one methyl group here and here. I can make it more complicated, right? Fine. Anyways, we're not going to do all that, right? So this, if you understood, so you just have to understand that in between eclipse and staggered, also I have some name of the confirmation called skew or gauche confirmations. That's what I need to know. I need you to know. Is it okay? Right? So everybody understood how is this staggered, right? And how not the other things are staggered. Yes.
Yes, sir, understood.
Yeah, cool. Right. So that is about your, now this conformational isomerism is not only going to happen in straight chain compound people, but again, what I'm going to tell you is not there in the syllabus. It is just extra knowledge, right? So the thing is, even in cyclic structures, okay, even in cyclic structures, this particular thing will happen, and it is more and more predominant in case of cyclic structures. Okay, now for example, I'll just give you one example, right? You have to know, right? So when I have cyclohexane people, right? When or let me take first the simplest of all, this thing. What is that? Cyclopropane I take. Okay, now there is a problem in cyclic compounds. Okay, now what is the problem with cyclic compounds is I know this each of the carbon atom is sp3 hybridized. That isn't it? All there are 4 bonds for this, right? So each of the carbon atom is sp3 hybridized, right? So if it is sp3 hybridized people, I know the shape, it should be tetrahedral. Okay, fine. Now what should be the bond angle? If it is sp3 hybridized and tetrahedral, what should be the bond angle? Let me see if anybody remembers.
The question was?
I'm asking in tetrahedral, not only in this molecule, if I have a tetrahedral shape, what is the bond angle?
So something around 110 degrees, sir.
Yeah, correct. Anybody wants to give me the perfect value? It is around 110, but what is the exact value? Yes, no, someone should remember. If you're really not answering, means you are wantedly keeping mum. One of you should remember this. Okay, let me ask. Maybe.
Sir, is it
Yes.
109 degrees?
Again,
So
not the exact.
109 degrees, 5 minutes.
Correct. I think something is there in the chat. Venetia told the answer, and yeah, correct, Rohan. Yes, it's 109 degree 5 minutes, right? That's the exact answer. Oops, sorry. Right, so I know that it is going to be 109 degree 5 minutes. Good. So most of you remember. Good, right? So what happens is, now if you check this bond angle, people, right? If you check this bond angle, what do you think is the bond angle? This is an equilateral triangle. Use your mathematics here and tell me what is the bond.
60
What is
degrees.
60 degree, right? 60 degree. Okay, see, where 60 degrees where 109.5 degrees where, right? So this molecule is sp3 hybridized, but it is not in tetrahedral shape. That's the point, right? So we know that if at all we want the molecule to have a stable structure, right? If at all I have sp3 hybridized molecule and I don't have any lone pairs on them, right? I know for sure that if at all I want a stable structure, VACPR theory says that I should have a bond angle of 109 degree 5 minutes. Right, but here what I see, it's having 60 degrees, no way close, almost half, less than half of them, almost less than half, isn't it? Right, so because of this kind of molecules are little unstable. They have something called as strain in them, right? They have something called as strain. Especially it's called angle strain because of the angle. So basically how do I put it? Let me switch on the video 1 second. So I'm just giving you a real life example. That's why I want to show my face. Here's the video. Okay, so hope you can see me, right? So it's like my hand is here. Someone has twisted it like this, and I will have to hold it like this only for my entire lifetime. Can you believe it? It's the same situation there, right? If it is like this, normal position, yeah, okay. I am in this stable, right? But someone has twisted my hand and I have to keep only like this for my entire lifetime. That's a strain, isn't it? You have to keep it, you like it's impossible for us, right? So the same thing will happen with molecules also. Hope you understand why am I saying that when you don't have the required bond angle, that ends up in a strain, right? Okay, so anyway, this is what I wanted to show you. Thank you guys. Okay, let me show the video. So where was it? Right, so I'm going to have angle strain here because it is supposed to be 109 degree 5 minutes, but it's no way close, right? It's 60 degrees, right? Okay, so this is going to have angle strain, but this is a small molecule, so it cannot do much anything about it. Okay, now actually I have to flip my screen also. Right, okay. Right. So now let me take, say, cyclobutane. Okay, cyclobutane I take. Okay, now what do you think is the bond angle here? Approximately, obviously, you don't have to give me this thing. So this is the assume that this is the square. So if it's a square, what is the bond angle?
90
now what is
degrees,
the angle?
sir.
90 degrees. Right. So you are little getting closer towards your 109 degree 5 minutes. This is 60. This is 90. So when you have cyclopentane, right? So there you will see it is little more closer, little more, say 100 and 105, like I would say 100 and 100. I can keep it as 100, right? But again, not closer. But when I go, so you see, when I go from here to here and from here to here, right? What you see is this angle strain decreases. Why angle strain decreases? Because the bond angle is getting closer and closer to the required bond angle. Okay, now when I go for this to this, okay, when I go for this to this, that is cyclopentane to cyclohexane, this is the most stable cyclic structure I can have. Please remember that. If I ask you, among 3, 4, 5, 6 membered rings, which is the one which is maximum stable, the answer is cyclohexane, because that has the least of all angle strings. That has the least of all angle strains. The bond angle is almost close to 109. I would say it's not 109, it's almost close to 105, 106. It just goes there, right? So the least of all angle strain is for what is that? Your 6-membered ring. When I go for a 7-membered ring, guys, if you just increase it to 7-membered ring, right? Now that is going to have a bond angle greater than 109 degree 5 minutes. Again, that is unstable. Hope you understand, right? When I'm going to have a 7-membered ring, right? So there, the bond angle is going to be higher than the required bond angle. In all the previous cases, you see that the bond angle is lesser than the required bond angle until 6. But after that, you will see that the bond angle is greater than 109 degree 5 minutes. Again, that is unstable. So out of all the membered rings, 6-membered ring is the most stable one. Okay, not 3, not 4, not 5, not 7 also. Because again, 7, you know what happens there. 8, again, it's going to be still more unstable, right? The most stable cyclic structure is a cyclohexane structure. Okay, fine. So anyways, why did I bring all this is because since this is since they are very much unstable, right? These three cannot do much anything about their angle strain. Okay, but your cyclohexane is really going to do something about the angle strain. It is going to do something. What is going to do? Nothing. It's just going to undergo the CC single bond rotations. Okay, all the single bond rotations I have, it can undergo, right? Obviously, I can get different conformations for cyclohexane, and nothing like that exists for all the other types of cyclic structures. Okay, now if you ask me, sir, how? So basically, this is not the way the molecule looks in reality. Cyclohexane doesn't look like this. It's not. So what you see here, this is planar, right? The entire all the carbon atoms are in this plane, in the plane of the car, in the plane of the laptop, right? So, but that is not how you see it is going to be in actual reality, right? So if you ask me, sir, then how is it going to look, right? Now, how is it going to look? Those are what are called as the conformations. How it actually looks is what is called as the conformations of cyclohexane. So anyway, I don't want to write it, so big word, right? So those are what are called as conformations of cyclohexane. So what are all the types of conformations? Like just like you had eclipse, staggered, gauche, here you're going to have different names, right? Say the first one is what is called as boat conformation. I think from the name itself, we can understand it is going to be in the form of a boat. Okay. Right, boat. I have a chair conformation. Right, these two are the most important. Other than that, I have something called as half chair. Right, half chair. I have something called as a twisted boat. Right, twisted boat. All these are the different names of the conformations of cyclohexane, only for cyclohexane, nothing else. Right, and you really don't have to know what are all these, but if you're interested, the most stable out of them all is the chair. Okay, most stable out of them all, the conformation, just like staggered is the most stable conformation, right? In case of the aliphatic compounds, just like the chair is the most stable conformation for cyclohexane. And do you want to see how it looks in reality? The chair, you want to see how it looks? Hmm? Do you want to see how it looks? I can draw it and show you. Do you want to see?
Yes, sir.
Ah, okay, fine. So this is how it's going to look, right? I need space. 1 second, guys. Right, so this is exactly how it's going to look. So you can see, right, this is like a chair, right, with the headrest. This is the headrest, right? This is the footrest, right? And this is where the person sits, right? So yeah, this is how it looks, the chair, right? So anyways, you don't have to know any of this if you're just preparing for your school exams. But if you're preparing for competitive exams, yes, all these are very, very important. Okay, right. So anyways, so you can understand how it looks, right? It's entirely different of what you draw on paper, and how it looks in reality is entirely different, isn't it? Right. So anyways, this is what is called as confirmation. Again, why do you think it happens? Is because of CC single bond rotations. That's the reason. CC single bond rotation. So it is going to take the most stable shape in that, right? And the most stable shape is the chair. Chair conformation, right? If you're interested, just type conformations of cyclohexane in Google. You will get all the pictures of how it looks if you're interested. If not, just you can leave it, right? Okay, guys, that's about your what is that? Isomerisms. Isomerism part I have completed. Done. Everything is done. Isomerism. IPAC naming you completed, and your isomerism also you're completed. Right. So after this, it is gonna be only the stability part, hyperconjugation, resonance, and all these stuff, right? So 753. Fine. Okay. Let me just give you the introduction. Right. So already gave you the flow chart, isn't it? I already gave you the flow chart of how an organic reaction happens. Right. So hope you remember there are going to be something called as substrates, right? There are going to be something called as substrates, right? Now these substrates are going to be attacked by something called as reagents, right? Now they both will react together, and they're going to form something called as intermediates, right? And I told you that these intermediates are unstable, right? So they will eventually gain something or lose something to form the final products, right? Okay, so this was the flow chart. So we studied about them now. When we studied about the substrates, we studied about how to name the substrates, and how what are the different types of isomerism I can have in the substrates. Substrates means the compounds, alcohols, ethers, phenols, acids, aldehydes, ketones, all these things, alkanes, all these things, right? We studied about everything, the isomerism part, the naming part, done, right? So this will come little later. Right now, we are going to concentrate on this, the intermediates. What can be the intermediates? What can be formed in between the reaction? You just see reactants and products, but you don't see what exactly is happening inside the reaction. That happening inside, the one of the things which is formed is what is called as the intermediates. Okay, right, fine. So now for us to understand this, right, for us to understand what do you mean by intermediates, I have to understand how bond fission happens in organic chemistry, right? We know what do you mean by fission. Fission is breaking, right? So you have to understand how a bond breaks in organic chemistry. right? Now, I can say that there can be two ways of visualizing bond fission or bond breaking, right? Anybody want to tell me what are the two types? You already know this, right, in your school? What is it? Okay, no, but there was no issues. So the thing is, I'm going to have two types called as homolytic bond fission, and obviously the other one is going to be heterolytic bond fission. Okay, homolytic bond fission and heterolytic bond fission. Okay, now we'll see. At least today we'll complete homolytic. Let us speak about heterolytic later. I mean tomorrow's class, right? So what happens in homolytic is, say, assume that I have a CC single bond. Okay, assume that I have a CC single bond. Okay, fine. The other three things also there, obviously. Right now, I am going to break this particular bond. Right? Is it so noisy outside? Oh god, I'm really sorry, guys. I'm really sorry about the background. Right. Okay. So anyway, so I am going to break this particular bond, right, in such a way, right? Obviously, you know that you are two electrons shared here. One electron coming from this carbon, another electron coming from this carbon. So they both would have come together to make this bond, isn't it? Right. So I am going to break this bond in such a way that the electrons are going to go where it came from. Again, I repeat, right? I am going to break the bond in such a way that the electrons are going to go where they came from. That means this electron is going to go to this carbon. This electron is going to go to this carbon. Okay, now how do you represent it? This is how you represent. Generally, if a complete bond breaks, you represent it like this, putting this arrow. That means both these electrons go to this carbon. Or say if you would have put it like this, that means both the electrons go to this carbon. But that is not the way you have to represent here, because it is not about two electrons. It's about one electron going to each of the carbon. So this is how you put. You're going to put a half arrow. Right? This is how you represent. Okay, so only a half arrow. Whenever you put a half arrow, that means I'm going to have homolytic bond fission. Okay, right. So obviously now what do you have? I see. I am going to have single unpaired electron, which is going to be on both these carbons. Right. So what? How do I represent it? Is like this. C, both these. C with the three things, and I'm going to put a dot. I'm going to put a dot like this. Obviously, the other one also is going to be same thing. 2 moles of this. Right now, what is this, guys? What is the name of this? Any idea? Whenever you have, sorry. This one. When I just formed the new one. This, when you break the bond, after that this is getting formed. What is it called as? Okay, no issues. Now, answer this question. When I have single unpaired electron in the molecule, in any molecule, did I tell you how they are called as? Just like this, you see, there is just one electron which is not paired. See, this is not a lone pair. Lone pair means I should have 2 electrons, right? So this is single unpaired electron which is there in the valence shell of this carbon. Right? So these kind of structures are what are called as free radicals, or in general they are called as radicals. I think we should have spoken about radicals in chemical bonding, but if not, you can know now. Right. So what is a radical? Radical is something. Radical is a species which has one single unpaired electron, which is not a bond pair, which is not a lone pair, single electron. Right. So those are what are called as free radicals. Right. So how do you get a free radical in organic chemistry? By making homolytic cleavage happen. Okay. So one of the intermediates, the first intermediate there are going to be 3 intermediates. The first one we found out, those are what are called as free radicals. Okay, right? So I think we'll stop with this today. Any questions? Any questions, people?
So could you repeat the definitions of free radicals?
Nothing. Free radicals are species having single unpaired electron. That's it. That's the definition. It's not a bond pair. It's not a lone pair. Single unpaired electron. One electron just there. Not a bond pair, not a lone pair. It's not paired basically at all. It's not a paired electron at all. Just a single electron, unpaired electron. Right? Those are what are called as free radicals. Okay, fine. Any other question, people?
No
Okay.
questions.
Fine. I suppose no questions. Well, I'll stop here. As again, we'll see tomorrow. I'll speak about heterolytic bond fissions. Okay, so there only you're going to see carbocations, carbanions, all these things are going to come in heterolytic bond cleavage, right? And then we'll see what are the different types of free radicals, different types of carbocations, different types of carbanions, and among these different types, which is more stable, right? And obviously for doing the stability problems, what are the tools we have? One tool I already introduced to you, that is resonance. Other than that, what other tools I have for determining the stabilities, right? And then yeah, this chapter is over with that. Okay, after that we'll go for hydrocarbons. Hydrocarbons little small. If you understand GOC, this particular chapter, that chapter is pretty easy. Okay, fine guys, thank you so much. We'll meet again tomorrow.
Thank you, sir.